Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. As you know, in our previous lecture we studied about the different instruments that are used for the detection of radiations. Particularly we studied about the Geiger molar counter. In this lecture we will study about the dose calibrator. A dose calibrator actually an essential instrument for the calibration of radiation in order to dispense into the patient. So if we see about the types of radiation detection, there are main two type of radiation detections are there. One is gas field detector and other is scintillation detectors. In gas field detector we use gas for the ionization purposes, which actually produce a pulse of current and give us information about the strength of the radiations and activity of the radiations. In other type of detection there is a scintillation detectors. These detectors actually have a semiconductor solid detectors that on receiving photons of energy emits electrons. These electrons then amplified and used for the detection and counting of radiations. In scintillation detectors there are gamma well counter, thyroid uptake probe, liquid scintillation detectors are being used. Yes, this is familiar to you about this graph. This graph is particular for the gas field tubes and gas field detectors, and we are continually studying this graph in order to proceed ahead. If there are different type of energetic radiation passes into the gas filled chamber, the ionization process occur, and this ionization process actually proceed pulse of current that is being used for the detection of radiations and strength of radiations, counts of radiations. So here is there are different regions of detection systems, like that ionization region, like that proportional region, and other is Geiger molar counter region. Limited proportionality region is not no more longer fruitful, because if you see in this region there are not a constant behavior of these two radiations or ionization processes. Here are two different lines are we can see here, but at the mid of this limited proportionality region, these two lines, these two current lines combine to each other and give a single line. So we can't achieve any kind of a particular information in this region, so this region is no more longer important for us. In this region, that is ionization region, that is directly related to the primary ionization that is being carried out by the incidence of the alpha radiation or beta radiation. Greater the energy of these two particles, greater would be the ionization process. If greater the ionization, greater would be the current. So this region actually is used for the dose calibration. So what is meant by dose calibration? A gas filled ionization chamber is act as a dose calibrator instrument. The question is that why do we needed dose calibrators? So the answer is very simple: used to measure the ionization radiations exposure of a given radioisotope. So how much ionizing radiations are there, or a researcher or a scientist or a worker which actually working in the area of radiations, how much radiation was exposed by that worker. So it is one thing that is being used, being available to calibrate how much a person are exposed to these radiations. In other, the important use of a dose calibrator is that in nuclear medicine, to measure the amount of radioactivity of a radionuclide before injection into patient. So it is very important to inject the radioactivity into the patient body after the calibration. If we don't use calibration, then no one know how much activity of radiation we have actually injected into the patient body, and that is not fruitful, but sometimes it will be more fatal for the patient as well as the oncologist. They are working in order to treat the patient. So calibrators are generally gas filled cylinders with the well in the center of the ionizing chamber into which the radioactivity is placed. So dear student, it should be in your mind, as you know, in our previous lectures we know there is a gas filled tube having a gas filled into the tube, which actually equipped with two electrodes. One is cathode and other is anode. Anode is a central wire, but cathode is a wall of the tube, and any incident radiation that is passes through the gas filled tube, that ionizing the radiation, ionizing the molecule inside the gas, that opposite ions like that electron and positive ions move toward their respective electrodes. Particularly the electron move toward the anode and they passes through the circuit and come discharge at the cathode. So this is a simple gas chamber, but if this is a well type gas chamber like that, here this is a gas filled into this chamber, and this is a open hole, and we put the sample into this, and the radiation that emitted from this activity, this radio pharmaceutical that emit different gamma radiation or beta radiation, that will passes through this wall into the gas environment. Here in this gas environment, these radiation, what actually doing, they are ionizing the gas molecules into electrons and positive ions, and definitely electrons attracted by the anode, and this attraction and this movement created current pulses. So in this regard, this system is used for the radioisotope calibration, radionuclide calibrators, Curie meter, activity meter, like that cobalt 57, barium 133, cesium 137, cobalt 60, and so on. So all these type of different instruments are being named to the dose calibrator. So next is the dose calibrator again. So these ionizing chamber radiation detectors are typically filled with the highly pressurized argon gas compressed up to around 50 atmosphere. So this is very important to know that how we use gas at very high pressure in this gas filled detectors, as which is actually used as a dose calibrator. So this is why, because this, if we see at high pressure organ, at low pressure organ, any incident radiation that will pass through this and pass through this tube, it is easily we can conclude that if a radiation passes through this, it will ionize only 1, 2, 3 or 4 molecules, but if the similar energetic photon passes through this type of tube, which actually have organ at high pressure, compressed organ is here, mean more and more molecules of organs present in this tube. So definitely what actually happening, the more molecule will be in the way of the radiation and more molecule will be ionized. So greater the ionization, greater would be the detection power and greater would be the pulse of that radiation processes. So in this regard we can say that able to measure activity anywhere from 1 micro curie to 20 curie. So this is a very low limit and this is very high limit. So this is due to the reason that the dose calibrator having a high pressure argon gas in it. Another way, the high compressed gas creates an ionic environment that favor the possibility of ionizing events more frequently as compared to the low pressure argon. There is a direct relation between the increased gas pressure and detection efficiency. So as I have discussed earlier that as you know, here are less molecule of argon gas in it, so less ionization will be there and less current will be produced. So if there is a less current will be produced, it's mean detection limit will be very less. So if there is energy that radiation that have very low amount of energy and have less ability, one or two, to ionize in this, because only one or two molecule come across into this environment, but here more and more molecule will be in its route of the incident radiation having low energy. So in this tube more molecule will be ionized, so that will be detected. So in this regard there is a direct relation between the increased gas pressure and detection efficiency. So this is the overlook and flow sheet diagram of dose calibrator, and this is a simple lead shielding, mean no radiation will pass through this shield to outside the into the environment, but inside there is a tube having a gas at high pressure, most probably that is argon gas, and inside is another wall. So this is open dipper that is we used into it and having a sample in it. So the sample will produce radiation, definitely it is continuously emit the radiation that will collected, that will passes through this gas filled tube, and if the gas is at high pressure more ionizing event will be occur, and it is more likely to detect at very low energy or low concentration, low activity radioisotope will also be detected, as well as a high activity radioisotope. So in this regard this is just this is like this and this system is like this. So in this regard we would be able to calculate or would be able to determine how much activity actually we are using to dispense into the patient body. So this is another well counter, and not using the gas filled tube, but there is using the sodium iodide crystal. This is a semiconductor dose calibrator in which the shape of the dose calibrator just like that of the dose calibrator having a gas filled, but instead of the gas filling here is a sodium iodide crystal. So the radiation emitted by the sample molecule and they are falling over to the collected by the sodium iodide crystal, and in lieu of these collection of radiation, these sodium iodide crystal produce for electrons, free electrons. These free electrons are then amplified through pre-amplification and so other processes, amplification and pre-amplification, and then they are converted into a pulse of current at very high level through photomultiplier tubes. So similar working is there as the dose calibrator used for of gas field detector are working to calculate the activity of a radioisotope. So these are different sample holder geometries and shapes that are being used inside this well. So these samples holders are used to put the sample into this well. Okay, so there are different shape. This shape is used to put the syringe inside this and in order to keep the syringe in aligned form, and like that. So this case is this case dipper. This case is a dipper, and this is holder. So actually this sample holder is we have put into the dipper, and this dipper is present in the hole of the gas filled tube. Okay, so why do we need to know the activity? We can estimate radiation absorbed doses to the organ by and whole body. So this is very important. Why we actually need to know the activity? If we are dispensing into the human body about 4 millicurie radioactivity we actually injected into the body. So in this regard we would be able to calculate the absorbed radioactivity by different organs if we know what actually the radioactivity we dispense into the human body initially. Dose depends on the activity, patient size, biodistribution of the specific radio-labeled drug. For a specific radio-labeled drug activity, a radiation dose to organ. So these are the different factors that depends on the dose that received by a patient body. So in order to calculate all these things, these factors, so there definitely we know about how much activity we initially injected into the human body. So how it works? Highly energetic photons interact in 3 direct ways. Photoelectric effect, exactly. These highly energetic photons interact with matter in 3 direct ways. One is the photoelectric effect, other is Compton scattering, other is pair production. In all of these interactions between photons and matter, energy is transferred, leaving ion pair behind. To collect the ion pair created from these interactions, the detector has an applied voltage with the negative cathode as the chamber wall and a positive anode within the ionization chamber as a wire or any other way. After ionization, positive charged ion drift toward the cathode and the negatively charged ions or electrons drift toward the anode. The positive and negative charge is supplied by a high voltage supply or a battery acting as a capacitor with the dose calibrator. This battery keeps the voltage on the cathode and anode constant and functions as a backup if there is ever a power outage to keep the calibration factor stored in memory. So it should be in your mind that if the potential difference between the cathode and anode is less, so most probably there is a recombination of ions may occur, but the potential is must be like that. No event of recombination of recombination of ionizing electrons and cations will occur. DC operates in the ionization chamber region of the voltage response curve where the ion pairs created by the radiation are collected. An increase in the voltage does not significantly increase the number of ion pairs collected. Yes, because we are discussing dose calibrating in the region of ionizing chamber. So here if we increase the voltage from this point to this point, you can see that the increase in voltage have no effect on the increase in current is constant. So in this regard, the increased voltage not affect the current, but it only is prohibited the recombination of the ions to form neutral molecule. An increase in the voltage does not significantly increase the number of ions pair collected. Number of collected ion pairs is constant, so the current is constant. Current that is generated and measured is also constant. Definitive ionization chamber platio. There is no increase in measured current because all ion pairs are collected and there is no recombination of pairs taking place. If a volume of gas is irradiated at a constant rate, a constant amount of ion pair are formed and constant current is generated. Definitely in this region constant number of ion pairs are generated and constant current is produced. So there are some advantages and some disadvantages of a dose calibrated. If we can study here, there is measuring the charge generated within the volume is that the current generated can be directly correlated to the radiation exposure. Similarly, a lack of information about individual ionization event or the energy generate the current. So this is a disadvantage. These are the advantages. And the activity of the source correlates with the characteristic radiation exposure of each radionuclide. Gas field detectors measures ionization created by photons. So other advantage is that the ionization platio collects all ionization events, avoiding dead time effects seen with well counter, able to measure high level of activity because it operates in current mode, which avoids dead time effect. If we see about the disadvantages of this, a lack of information about individual ionization event or the energies generating the current. This makes it impossible for the dose calibrator to identify or distinguish radionuclide in mixture or contaminated samples. So have no any particular type of distinctions. A solid sodium iodide crystal directly detect discrete decay events. So used for counting swipes for around the work area to detect small traces of contaminations. So this is another disadvantage. Not only it detect the sample actually holding inside the dipper, but also around if there is any contaminated radioactivity in the laboratory present in vicinity of this dose calibrator, it also detect these contaminated tracer radioisotope tracers. Allow for energy discrimination and presentation of energy spectra of a sample. So these are the disadvantage. What is the dead time effect? If there is a dead time to measure the current pulses, so occur when operating in pulse mode. So dead time, only effective when there is a pulse mode, like that. Just in this regard, this is one pulse, this and this is dead time, this is other pulse, this is other pulse. So this is the dead time. So it also affect the measuring process of the radioactivity. So sodium iodide crystal used in well counter operates in pulse mode to capture ionizing events. So each energy event creates a voltage plus pulse. If the pulse are too frequent as from a high activity sources, the detector is unable to count the pulses quickly enough and they begin to blend into one another. So if there is energy like that, this is a tube, I'm just showing this is a tube, and big amount of energy like that this come into this tube, so it is unable for the detection to make it a proper calculation, make it proper pulses. But if there is a small amount of radioactivity that it have to detect, then there is a proper and regular pulses will be obtained, and we would be able to calculate properly each pulse of current. But in case of high bursting of radioactivity, in this case what actually happening, like that such type of pulses will be occur. Okay, and this one, and this one, this one, this one. So each pulse is actually overlapping with each other, and would not be able to calculate good way to how much activity actually we are going to measure. So this is a drawback of dead time mode for the calculation process. Okay, in the pulses are too frequently as from a high activity source, the detector is unable to count the pulse quickly enough, and they begin to blend into one another, overlapping over one another. This is problematic because information is lost, and the resultant measurement is not a true representation of the activity of the source. The dose calibrator does not directly measure the energy of a radionuclide, only the current generated from ionizing events, and the measurement is not affected by this problem. So the activity of the material is measured in terms of ionization current produced by the emitted radiation which interact in the gas. The chamber is sealed, usually under pressure, and has two coaxial cylindrical electrodes maintained at a voltage difference derived from a suitable supply, the axial space constituting the well. Okay, in the electrometer, the ionizing current is converted to a voltage signal which is amplified, processed, and finally displayed, commonly in digital form in the form of activity, becquerel, or Curie, as we have seen in first, third, or fourth, like that. Just come to point this, like so, appear in the form of these numeric values after proper calculations through amplification, range selector, isotope correction, and display appear on this meter in the form of numeric values. Okay, like that here. Okay. Response of the detector will depends. So what the response of the detector will depends on different factors, but radionuclide energy of photon, if the greater the energy of the photon beyond the limit. So we in this process we study that if there is a high amount of if pulses are too frequent, the detector unable to count the pulses quickly enough and to begin the blind into one another. This process actually, in what environment we obtain such type of difficulties, when there is a heavy burden of radiation actually received by our detector. So in this regard, pulses overlap with one another. So this is other factor that actually affect the detection mode. So energy of the photon is very important. So energy of photon should be in a range that is selected, that is mentioned for that type of dose calibrated detector. Geometry of the detector, that is also important. Geometry of the source also important, and the condition of the instrument. Geometry efficiency of dose calibrator, if number of photons reaching the detector and the number of photon emitted from the sample ns. Okay, so then geometry efficiency would be like that, the number of photon reaching the detector divided by number of photon emitted from the sample. So if the sample number of photon emitted by the sample is equal to the number of photon detected by the detector, so it is efficiency is 1. But if sample is emitting 100% radiations, but it receives only 50%, the efficiency will be reduced to half. So like that. So this is not a good geometry. This is also not a good geometry. This is a very good geometry, because maximum number of energy photons are received by the detector, and in this most of the radiations going away from the gas tube and not received by the detector, and in this geometry most of the radiations exposed to open environment, not to the detector system. So this is not a good efficient geometry, so this is efficient geometry. So this is gamma counter a flow sheet diagram as we have studied again. This is probe system. In this that is used for the calculation of thyroid gland radiations. So this is a probe, and this is put at the place of the organ, and the organ generate the radiation received by this sodium iodide crystal. Sodium iodide crystal emitted the electron are received by photomultiplier tube. These photomultiplier tubes exponentially increase the number of photons that make a great impulse of current, and this is this pulse of current pre-amplified and then amplified and then analyzed into reasonable counts. So other is the liquid scintillation counter. This is also important in order to study different type of radiations. So dear students, this is about the dose calibrator. Inshallah we will see you in our next lecture. तब के लिए अल्लाह हाफिज़.